Have you ever wondered how a nuclear reactor makes electricity? It's not as mysterious as it sounds. It's all about moving heat. A pressurized water reactor, or PWR, is basically a very powerful and very controlled way to boil water. At its core, a reactor is a giant heat machine. It creates an incredible amount of heat through a process called nuclear fission. This is where tiny atoms split apart and release a massive amount of energy. But that heat is only useful if we can move it to where we need it. This is where the science of heat transfer comes in, and it's one of the most important jobs inside a reactor. Think of it like cooking on a stove. The burner gets hot, but that heat needs to travel through the metal of the pot to cook your food. In a PWR, the burner is the nuclear fuel. The food is the water that will eventually turn into steam and spin a turbine. If we can't move that heat efficiently, the reactor can't make electricity. Worse, if the heat gets stuck and builds up in the fuel, it can cause major problems. So, understanding how heat moves is not just about making power, it's the key to keeping the entire system safe and running smoothly. The whole point of a PWR is to harness the energy from fission. This energy first appears as heat, right inside the nuclear fuel. We need a way to grab that heat and carry it away. The carrier is water, but it's kept under extremely high pressure. This high pressure is what gives the pressurized water reactor its name. It stops the water from boiling, even when it gets super hot. This hot pressurized water then flows to another part of the plant to boil a separate loop of water, creating the steam needed for electricity generation. The entire process is a carefully choreographed dance of heat transfer from one place to another. So, in every single moment a reactor is operating, a silent but powerful process is happening. Heat is constantly being generated, moving through different materials, and being carried away. Mastering this flow of energy is the fundamental challenge of nuclear engineering. It dictates how much power the reactor can produce, how efficiently it operates, and most importantly, how safe it is. It's a fascinating world of physics and engineering working together, ensuring that the immense power locked inside the atom is used for good. Let's dive into how this amazing process works, step by step. To understand how a reactor works, we first need to know the two main ways heat moves around. The first one is called conduction. Imagine you're holding a metal rod and you stick one end in a campfire. After a little while, the end you're holding will start to feel warm, right? That's conduction. Heat is traveling directly through the solid material. The tiny particles in the metal get energized by the fire and start vibrating like crazy. They then bump into their neighbors, passing that energy along, particle by particle, all the way down the rod to your hand. It's like a chain reaction of jiggling atoms. In a nuclear reactor, conduction is the first step. The nuclear fuel is made of small ceramic pellets. When fission happens inside these pellets, they get incredibly hot. This heat then travels from the center of the pellet to its outer surface through conduction. The pellets are stacked inside long metal tubes called cladding. Heat then has to conduct through the cladding material to reach the water flowing outside. So, conduction is all about heat moving through solid objects. It's the essential first leg of the heat's journey out of the fuel. The second way heat moves is called convection. This happens in fluids, like liquids and gases. Think about boiling a pot of water. The water at the bottom gets heated by the stove through conduction. As it gets hotter, it becomes less dense and rises to the top. The cooler, denser water at the top then sinks down to take its place, gets heated, and rises again. This circular motion is called a convection current. It's a super effective way to mix the fluid and spread the heat around much faster than conduction alone could. Convection is the star of the show in a PWR. Once the heat has conducted through the fuel and the cladding, it reaches the water. This water is constantly being pumped through the reactor core at a very high speed. As the water flows past the hot fuel rods, it picks up the heat. This isn't a passive process. The moving water actively carries the heat away with it. This massive movement of hot water is a giant convection system. It's what transports all that powerful fission energy out of the reactor core and over to the steam generators. Conduction gets the heat to the surface, and convection takes it from there. Science has a rule book for everything, and heat transfer is no exception. These rules are written in the language of math, in what we call governing equations. For conduction, the main rule is called Fourier's law of heat conduction. It sounds complicated, but the idea is simple. It says that the rate at which heat moves through a material depends on three things. First, the material itself. Some materials, like metals, are great conductors, while others, like plastic or ceramic, are poor conductors. This property is called thermal conductivity. Second, Fourier's law depends on the area. The bigger the area the heat can flow through, the more heat can move. Think of it like a highway. A 6-lane highway can handle more cars than a 1-lane road. So, a wider fuel rod could transfer more heat than a narrow one. Third, it depends on the temperature difference or temperature gradient. The bigger the difference in temperature between the hot side and the cold side, the faster the heat will flow. Heat is always trying to move from hot to cold to even things out, and a big temperature difference gives it a bigger push. For convection, the main rule is Newton's law of cooling. This equation helps us figure out how quickly heat transfers from a solid surface to a moving fluid, like from the fuel rod cladding to the water. Just like Fourier's law, it also depends on a few key things. First is the surface area. A larger surface area means more space for the water to touch the hot rod, allowing more heat to be carried away. This is why some heat exchangers have fins, to increase the surface area and improve heat transfer. The second part of Newton's law of cooling is the temperature difference between the surface of the cladding and the bulk temperature of the water flowing by. A hotter rod surface compared to the water temperature will result in a faster rate of heat transfer. The final and very important piece is the heat transfer coefficient. This number tells us how good the convection process is. It depends on many factors, like how fast the water is flowing and what its properties are. A fast-moving, turbulent fluid will have a much higher heat transfer coefficient than a slow, calm one. So we have these great equations, but they need some starting information to work. This information is called boundary conditions. Think of it like using a GPS. You need to tell it your starting point and your destination to get directions. For heat transfer problems, boundary conditions are the starting points and destinations for the heat. They define the temperature or heat flow at the edges, or boundaries, of the system we are looking at. Without them, our governing equations are just abstract formulas with no connection to the real world. In a reactor core, we have several important boundaries. One key boundary is the very center of the fuel pellet. Because the pellet is symmetrical and heat is generated evenly, the very center is the hottest point. At this exact center, the heat flow is zero. Heat is flowing away from the center in all directions, but not across the center itself. This is a type of boundary condition called a symmetry or zero flux boundary. It gives us a known starting point for calculating the temperature profile across the entire fuel pellet. Another critical boundary is where the fuel rod's cladding meets the cooling water. This is the interface where conduction stops and convection begins. Here, we can set a boundary condition based on Newton's law of cooling. We know the temperature of the water flowing by. We measure that. And we know the properties of the flow. This allows us to connect the temperature of the cladding surface to the rate of heat being carried away by the water. This boundary condition is essential because it links the solid part of the system, the fuel rod, to the fluid part, the coolant. Why does this all matter so much? Because boundary conditions control the entire temperature landscape of the reactor core. If the temperature of the incoming coolant water changes, that's a change in a boundary condition. This change will ripple through the whole system, affecting the cladding temperature and even the temperature at the center of the fuel. By carefully controlling these conditions, like the coolant flow rate and its inlet temperature, operators can manage the reactor's power level and ensure that no part of the fuel ever gets too hot. They are the control knobs for the entire heat transfer process. Let's follow the incredible journey of heat as it travels from the heart of the fuel to the cooling water. It all begins inside a tiny ceramic pellet of uranium dioxide. When a uranium atom splits, it releases a burst of energy, making the pellet sizzle with heat. We're talking temperatures over 1,000 degrees Celsius, about 1,800 degrees Fahrenheit, right at the very center. This intense heat now needs to get out. Its first challenge is to travel from the super hot center of the pellet to its outer edge. This happens entirely through conduction, moving particle by particle through the solid ceramic material. Once the heat reaches the surface of the fuel pellet, its journey isn't over. There's a very tiny gap between the pellet and the metal tube, or cladding, that surrounds it. This gap is filled with a special gas, usually helium, which is a good conductor of heat. The heat must conduct across this small gas gap to reach the inner wall of the cladding. From there, it conducts again, this time through the solid metal of the cladding itself. The cladding is usually made of a zirconium alloy, a material chosen because it's strong and transfers heat well. Now for the final, and honestly, most dramatic step. After traveling through the cladding, the heat finally reaches the outer surface of the fuel rod. Here, it meets the cooling water, which is rushing past at an incredible speed. This is where the handoff from conduction to convection happens. The heat instantly transfers from the solid cladding surface into the moving fluid. The water, kept under immense pressure to prevent it from boiling, grabs this heat and carries it away. This process is extremely efficient because the water flow is turbulent, constantly mixing and bringing cooler water into contact with the hot rod. The water, now carrying a huge amount of thermal energy, flows out of the reactor core. It continues its journey to a piece of equipment called a steam generator. Inside the steam generator, the super hot, high-pressure water flows through thousands of tubes. On the other side of these tubes is a separate loop of water at a lower pressure. The heat conducts through the tube walls and causes this secondary water to boil violently, creating the high-pressure steam that will spin the turbines and generate electricity. The original water, now cooler, is pumped back to the reactor core to pick up more heat, completing the cycle. Making a nuclear reactor more powerful or more efficient often comes down to one thing: improving heat transfer. If you can get heat out of the fuel faster, you can generate more heat in the first place without overheating the system. So nuclear engineers are always looking for clever ways to enhance heat transfer. One common method focuses on the coolant itself. By increasing the speed, or flow rate, of the water moving through the core, you can improve convection. Faster moving water creates more turbulence, which scrubs more heat off the fuel rods. Another strategy is to change the surface of the fuel rods. Remember Newton's law of cooling? It tells us that a larger surface area leads to better heat transfer. While we can't just make the fuel rods infinitely wide, we can add features to their surface to increase the area. Some advanced designs incorporate tiny fins, ribs, or grooves on the cladding. These features, sometimes called surface enhancements, increase the effective surface area that the water comes into contact with. They also help to trip up the flow of water near the surface, creating more turbulence and further boosting the heat transfer coefficient. We can also improve things on the conduction side of the equation. The small gap between the fuel pellet and the cladding is a bottleneck for heat. It's filled with helium gas because helium is a better conductor of heat than most other gases. But what if we could do even better? Some advanced fuel concepts are exploring ways to eliminate this gap entirely by bonding the fuel directly to the cladding. This would create a seamless path for conduction, dramatically lowering the temperature inside the fuel pellet and making the whole process more efficient. Even the fuel material itself can be improved. Standard uranium dioxide fuel is a ceramic, which isn't a fantastic conductor of heat. Researchers are developing new types of fuel with higher thermal conductivity. For example, adding materials like silicon carbide to the uranium fuel can create a composite that transfers heat much more effectively. A fuel that can move heat to its own edge faster means the center of the pellet stays cooler for the same amount of power generation. This provides a bigger safety margin and allows the reactor to be pushed to higher performance levels. So why do we go to all this trouble to enhance heat transfer? There are two huge reasons: safety and efficiency. Let's start with safety, which is always the #1 priority in nuclear power. The biggest danger in a reactor is the fuel overheating and melting. The temperature of the fuel is determined by a balance, the heat being generated by fission versus the heat being carried away by the coolant. If you improve heat transfer, you are strengthening the heat carried away side of that balance. This creates a larger margin of safety. For every material in the reactor core, there is a maximum temperature it can safely handle. The cladding can't get too hot, or it might corrode or burst. The fuel pellet can't get too hot, or it might swell or melt. By enhancing heat transfer, we can run the reactor at a high power level while keeping all the components well below their temperature limits. This means that if something unexpected happens, like a temporary reduction in coolant flow, there's a bigger buffer before temperatures reach a dangerous level. It's like lowering the water level in a bathtub to make sure it doesn't overflow. Now for efficiency. A more efficient power plant is one that gets more electricity out of the same amount of fuel. Better heat transfer helps achieve this in a few ways. First, a reactor that can safely run at a higher power level simply produces more electricity. This is called a power uprate. Many existing nuclear plants have been able to increase their power output by making targeted improvements to their heat transfer systems. It's like getting a more powerful engine in your car without having to buy a whole new car. Furthermore, the overall efficiency of any thermal power plant is related to its operating temperature. The hotter you can make the steam that drives the turbines, the more efficient the whole process becomes. By improving heat transfer in the reactor core, we can produce hotter water in the primary loop. This, in turn, allows us to create higher temperature, higher pressure steam in the secondary loop. This higher quality steam can spin the turbines more effectively, converting a larger fraction of the original heat energy into useful electricity. It means less wasted heat and more power for our homes. Let's make this real with some simple examples. Imagine a fuel rod surface is 350 degrees Celsius, and the water flowing past it is 300 degrees Celsius. The temperature difference is 350 minus 300 equals 50 degrees Celsius. According to Newton's law of cooling, the heat flow is proportional to this difference. Let's say our heat transfer coefficient is 20,000 watts per square meter per degree Celsius, a typical value. If the surface area is 1 square meter, the heat being transferred is 20,000 watts per square meter per degree Celsius times 1 square meter times 50 degrees Celsius, which equals 1 million watts, or 1 megawatt. That's a huge amount of power from just 1 square meter of surface. Now, let's see what happens when we enhance heat transfer. Suppose we add some tiny fins to the surface, increasing the effective area by 20% to 1.2 square meters. Suddenly, our heat flow becomes 20,000 watts per square meter per degree Celsius, times 1.2 square meters, times 50 degrees Celsius, which equals 1.2 million watts, or 1.2 megawatts. That's a 20% increase in power transfer just by changing the surface geometry. Alternatively, we could get the same 1 megawatt of heat transfer, but with a lower surface temperature. This shows how enhancements can either boost power or increase safety margins by lowering temperatures. Let's look at conduction inside the fuel pellet using Fourier's law. The law can be simplified to say that the temperature drop across a material is equal to the heat flow rate times the thermal resistance. Resistance is like a measure of how hard it is for heat to get through. A material with low thermal conductivity, like standard uranium fuel, has a high thermal resistance. Let's say it has a resistance of 0.0001 degrees Celsius per watt. If 1 megawatt of heat is flowing through it, the temperature drop from the center to the edge would be 1 million watts times 0.0001 degrees Celsius per watt, which equals 100 degrees Celsius. Now imagine we use an advanced fuel with better thermal conductivity, cutting its thermal resistance in half to 0.00005 degrees Celsius per watt. For the same 1 megawatt of heat flow, the temperature drop is now just 1 million watts times 0.00005 degrees Celsius per watt, which equals 50 degrees Celsius. This means the center of the fuel pellet is a full 50 degrees cooler than before, even while producing the same amount of power. This is a massive safety improvement. It demonstrates mathematically how a better conducting fuel can make a reactor safer and more robust, all thanks to the simple rules of heat transfer. From the fiery center of a uranium pellet to the spinning turbines of a generator, the story of nuclear power is a story of heat transfer. It's an invisible but constant dance governed by the fundamental laws of physics. We've seen how conduction passes heat through solids, like a baton in a relay race, from the fuel's core to its outer cladding. Then, we saw how convection takes over, as fast-moving water swoops in to carry that immense energy away from the reactor core. This two-step process is the engine that drives every pressurized water reactor on the planet. Understanding the rules of this dance, the governing equations of Fourier and Newton, is not just an academic exercise. It is the key to designing, operating, and improving these incredible machines. By defining the temperatures and heat flows at the boundaries of the system, engineers can predict and control the behavior of the entire reactor. This mastery allows them to ensure that the powerful process of nuclear fission remains safely contained and efficiently harnessed, keeping all components well within their operational limits while maximizing power output. The quest to enhance heat transfer is a continuous journey of innovation. Whether it's by adding fins to fuel rods, developing more conductive fuels, or simply optimizing the flow of coolant, every improvement pushes the boundaries of what is possible. These enhancements are not just about chasing numbers. They translate directly into tangible benefits. They create reactors that are safer, with larger margins to handle unexpected events. They lead to plants that are more efficient, capable of generating more clean electricity from the same amount of fuel. In the end, the complex science of heat transfer boils down to a simple, elegant purpose: to safely and reliably move energy from where it's created to where it can be used. It is the unseen force that transforms the power of the atom into the electricity that lights our cities and powers our lives. By continuing to explore and master this science, we can ensure that nuclear energy remains a safe, clean, and vital part of our global energy future, all thanks to the remarkable journey of heat.